The universe is being pulled towards something. The galaxies are sliding, all of them, like iron filings tugged across a table, only the magnets buried under our own Milky Way. We can't look straight at it. Dust and gas in our galactic plane turn the sky into a blackout curtain, and behind that curtain something is pulling us at hundreds of kilometers per second. Telescopes argue. Maps don't agree with the motion. The names we gave the sky don't match the forces underneath. So we start with a chase. Find the pull, weigh the push from a vast void, test the rumors, redraw our home, and see where we're really headed. The pull we couldn't name, Great Attractor, emerges. Start with a number that won't sit still. The cosmic microwave background has a hot side and a cold side, our dipole. Subtract the expanding universe, and what's left says the local group is moving at roughly 600 kilometers per second toward somewhere in the constellations of Centaurus and Norma. That's not a drift. That's a decision written in velocity. Astronomers tried to point at the culprit, but the line of sight ran through the Milky Way's worst neighborhood, the Zone of Avoidance, thick lanes of dust and gas that blot out galaxies in visible light. For decades, the most suspicious part of the sky was the part we literally couldn't see. So people did what they do when a road is closed. They found another way around. Radio waves at 21 centimeters slip through dust. Near-infrared light punches harder than optical. X-rays ignore the smog and light up the hot gas in galaxy clusters. Piece by piece, a pattern bled through the fog. Get this? When the static cleared, a heavyweight stepped forward. The Norma cluster, also called Abel 3627, massive and hot, hiding near the galactic plane. Around it, walls of galaxies, Centaurus structures stretched like beams in a scaffold. The community gave the collection a name that sounded like a destination, the Great Attractor. It felt right. It explained the arrow on our velocity vector. It explained the weirdness in galaxy counts pointing that way. It gave journalists a headline. But the numbers wouldn't settle because flows hinted at something deeper downstream. Here's where it gets tricky. How do you weigh something you can barely see? You infer distances. You stack different distance ladders, Tully, Fisher for spirals, surface brightness fluctuations for ellipticals, type Ia supernovae when you're lucky. Then you compare the redshift velocity to the distance to peel away the Hubble expansion and expose the peculiar motion underneath. Every rung comes with biases, Malmquist, selection, extinction, and if you're off by a few percent, your flow field tilts in the wrong direction. Teams fought over footnotes. Calibrations weren't just technicalities, they were compass needles. Meanwhile, more of the map came into focus. The Vela Supercluster peeked out from behind the dust. The Centaurus wall traced a path that didn't stop at Norma. The attractor started to look less like a single monster and more like a confluence of structures stacked along our line of sight, strung on filaments, layered behind the Zone of Avoidance. Was the Great Attractor a place or a mirage made from overlapping walls? Then a larger shadow entered the conversation. The Shapley Supercluster, SCL 124, deeper, richer. Farther downstream on the order of 650 million light-years, Z approximately 0.046. Redshift surveys counted clusters, X-rays measured their heat, and weak lensing began to feel the dark matter scaffolding. If Shapley was that heavy, maybe the Great Attractor was just midstream, a rapid on the way to a waterfall. This was the moment everything changed. Flow reconstructions grew more sophisticated. Instead of piling up galaxy counts, astronomers rebuilt the velocity field itself, using thousands of peculiar velocity measurements to infer where matter had to be. Think of it like mapping the shape of a riverbed by watching the ripples and eddies on the surface. Where the water converges, you've got a valley and a tractor. Where the water diverges, you're sitting on a hill, a repeller. Coherent streamlines started to run past the Great Attractor's basin and bend toward Shapley's deeper well. The destination name didn't fit anymore. The Great Attractor looked like a saddle point, flat-bottomed in places, yes, but not the deepest drop. Unknown to most viewers of those first maps, a second piece was forming off-stage. The numbers hinted our motion wasn't only about pull. There was a missing part of the speed budget. Something else had to be shaping our path, something we weren't counting because we weren't looking for it. Meanwhile, back at the Zone of Avoidance, radio astronomers were still finding galaxies where star counts said there shouldn't be any. Each detection tightened the picture. Each extinction correction shaved error bars. You could feel the community moving from myth to measurement. A micro-story from that era. An observing run aimed through the plane, the spectrum smeared with foreground hydrogen. The astronomer holds the printout under a lamp in the hallway. One narrow 21-centimeter spike stands above the noise, a galaxy hiding behind the brightest part of our sky. Someone laughs, not because it's funny, but because the universe left a breadcrumb right where the map said, "Here be dragons." By the late 2000s, the lore had shifted. The Great Attractor remained in the lexicon, but it wasn't an answer. It was a clue. Our CMB dipole still pointed roughly that way, but the physics asked for scale and context. You needed the walls we could finally see, the clusters we could weigh in X-rays, and the far-off anchor of Shapley to make sense of the vector. And you needed to accept an uncomfortable idea. That absence could matter as much as presence. That the empty parts of the map might steer the currents as strongly as the crowded ones. While that was happening in Centaurus and Norma, a question gathered on the far side of the sky. If something pulls us, what's pushing from behind? That's where the next chapter begins. The map that moves, peculiar velocities and hidden currents. To understand the push, we had to get ruthless with motion. Start by taking the universe's expansion off the table. Every galaxy's redshift is a mix of two things: the Hubble flow that stretches space itself, and a smaller, messier term called the peculiar velocity, how the galaxy swims through that stretch. Subtract the expansion cleanly and the leftovers sketch the hidden currents. But get this wrong by a hair and you tilt the whole river. So the community went ladder by ladder, rung by rung. For spiral galaxies, the Tully-Fisher relation linked rotation speed to intrinsic brightness. Spin fast, shine bright. If you know how bright it should be, its observed brightness tells you the distance. For ellipticals, surface brightness fluctuations measured the pixel-to-pixel grain in a galaxy's light. Nearer galaxies look clumpier, farther ones smoother. When lucky, Type Ia supernovae offered standard candles that lit the way across deeper gulfs. Each method carried baggage. Selection affects skewed samples toward brighter, easier targets. Malmquist bias made you overcount luminous outliers at larger distances. And a zone of avoidance, dust shaved photons off every estimate, demanding extinction corrections that could quietly warp the results. Here, where the map got clever. Cross-matching became a survival tactic. HI surveys at 21 centimeters pulled in galaxies the optical catalogs missed. Near-infrared catalogs, less sensitive to dust, recalibrated distances in the dirtiest parts of the sky. X-rays flagged clusters you'd never see in starlight alone, their hot gas advertising deep wells of gravity. Then, with thousands of imperfect distance, velocity pairs, researchers built a velocity field, often with Bayesian or Wiener filter reconstructions that tame noise but keep the bones of the flow. The idea was simple. If nearby points all drift in the same direction after you strip out Hubble's expansion, something real is steering them. And a pattern formed. Velocity vectors lined up across swaths of the sky, not as random gusts but as a steady wind. The arrows near the Great Attractor region leaned that way, sure, but they didn't stop there. Streamlines, those imagined threads a leaf would follow, ran past the nominal basin around Norma and Centaurus and bent toward deeper structure. You could trace them like watershed lines on a topographic map. Where flows converged, you marked an attractor. Where they sheared, you drew the boundary between basins. What nobody knew at the time was how much the zone of avoidance had been sanding off the truth. Correct for extinction with infrared data, and some arrows pivoted a few degrees. Fold in HI detections behind the plane, and entire filaments snapped into place. A micro-story, A team reprocessed a patch near Vela with updated dust maps. The distance moduli shifted by tenths of a magnitude, small on paper. On the flow map, a cluster's peculiar velocity flipped sign, from slight approach to slight recession. That single flip nudged a chain of arrows and erased a phantom eddy that had anchored 3 years of conversation. Meanwhile, statistical landmines kept popping. Malmquist bias wanted to inflate distances for galaxies near your detection limit, faking an outward flow. Cuts meant to avoid it sometimes carved away the very structures you hoped to trace. The zone of avoidance turned crowded. HI line profiles blended, source confusion rose, and velocities of foreground gas smeared clean signals. So the field leaned on redundancy. Independent teams, different instruments, overlapping sky. If a flow feature survived 3 measurement methods, it earned its contour on the map. Then came the reveal that tightened the knot from pillar I when you stitched the best data together. The coherent stream pointed past the Great Attractor toward a deeper sink, aligning with reconstructions that would later define Laniakea's basin. Water doesn't stop at a midstream rapid. It glides through and heads for the valley. The flow lines trended toward the Shapley Concentration far downstream. The Great Attractor's gravity mattered locally, but the riverbed sloped on. Unknown to them, across the other side of the sky, underdensities were shaping the same currents. The reconstructions hinted at divergence zones, places where streams peeled away. At first, teams described lack of pull. Later, they realized it felt like a push. But that language fight belonged to the next act. For now, the lesson was blunt. Peculiar velocities aren't noise. They're the handwriting of structure on the expanding page of space. Clean the measurements, tame the biases, and the map starts moving. And once the map moves, it points, not at where we thought the journey ended, but at where the current insists we're going. The Dipole Repeller, the push we didn't expect. While the flow lines were threading past the Great Attractor toward Shapley, something else was carving the same pattern from behind. At first, it was a sentence people tossed into talks. There's less mass over here. But it didn't sound like a force. Then teams started rebuilding the map from motions alone, and the empty part of the sky stopped being a footnote. It became a driver. Here's the counterintuitive bit. Gravity only pulls. There's no anti-gravity in this story. But if one region is underdense, thinner in galaxies, thinner in dark matter, then surrounding mass exerts a stronger pull than the void side. Matter flows away from the low toward the high. Stand on a hill in a river and water will seem to push off you, even though gravity is pulling it downhill somewhere else. That's the repulsion in quotes, an effective push born from an absence. To make that idea more than a metaphor, you need to turn noisy velocity arrows into a 3-dimensional field. That's what the reconstructions did. Start with thousands of peculiar velocity measurements, galaxies and clusters with distances good enough to subtract Hubble's expansion. Feed them into a Bayesian or Wiener filter algorithm that assumes flows in the linear regime trace the gradient of a potential. Out comes a smoothed velocity field and, by inversion, a density field. Valleys where flows converge, hills where they diverge. In early 2017, Yehuda Hoffman, Daniel Pommard, R. Brent Tully, and Haleen Courtois pointed to a pattern that had been sitting inside those reconstructions. One side of the sky behaved like a classic attractor, Shapley's mass pulling streamlines in. The opposite side behaved like a hilltop. Flows peeled away from a vast, nearby underdensity. In their maps, the local group's motion and the direction of the cosmic microwave background dipole could be reproduced by a tug-of-war. Shapley on one end, a supervoid on the other. They called that emptiness the Dipole Repeller, no new force, just gravity acting on contrasts. The word did work it wasn't supposed to. Repeller sounded like a new force. The physics was old-fashioned gravity. In seminars, people fought over language. Was repeller an invitation to misunderstand? Or was it the clearest way to name a real feature of the flow, the divergence where galaxies accelerate away because there's simply less to hold them? Hoffman's team leaned into clarity. No new physics, no exotic fields. Just flows from empty to full, with the underdensity playing the role of a hill that water can't sit on. Meanwhile, something else clicked. The direction of that effective push roughly aligned with the local group's motion out to tens of thousands of kilometers per second in redshift space. That's technical speak for scale. The pattern held over a lot of cosmic real estate. If you plotted the bulk flow vectors as you stepped outward, they lined up against the repeller and toward the attractor like a compass needle trapped between two magnets, except the north wasn't a mass at all. It was a lack. A human beat from those weeks. A researcher walks into a colleague's office with a printout of the reconstructed streamlines. Two colored bundles, one curving toward Shapley, one bending away from the void. If this is right, they say, we've been explaining half our speed with only half the causes. The colleague stares, then asks the question the word repeller forces. Are we telling people gravity pushes now? The answer is patient. We're telling them emptiness lets other pulls win. Of course, the detection carried caveats. The predicted position of the repeller sat in a region thinly covered by redshift surveys. The void itself was hard to catalog with galaxies because it's defined by their absence. Algorithms that identify voids disagree about boundaries. Thresholds move edges around. But the velocity-based signal didn't care about seeing the void directly. It cared about coherent divergence in the flow, about where the arrows refused to point. Then came the payoff. Fold the repeller into the budget and the residuals shrink. The mismatch between the observed CMB dipole and the pull from known overdensities eases. The local shear, how quickly neighboring streamlines change direction, makes sense if you place a hill under one side of the map. Even skeptics who disliked the branding had to engage the balance sheet. Subtract the contribution of the underdensity and the numbers wobble. Add it, and they settle. There's a deeper lesson hiding in that accounting. When we talk about structure, our eyes go to clusters lit in X-rays, to bright filaments strung with star-forming knots. But the universe's scaffolding is a set of contrasts. Ridges and valleys need empty slopes between them. The dipole repeller is a reminder that those slopes aren't passive backdrops. They steer everything that flows nearby. Meanwhile, something else was stirring on much larger scales. A claim that there might be a current beyond even Shapley and any local void, a drift that ignored the map's edge. If pull explains our motion, what do we make of a rumor that says the whole pool is sliding in one direction? That's where the controversy walked in with a microphone. Dark flow, a claim too big to ignore. Here's the rumor that wouldn't sit down. What if everything, clusters hundreds of millions of light years apart, was drifting the same way, as if the whole pool had a tilt we couldn't see? Not a local nudge from Shapley, not the push of a nearby void, a current on scales the map didn't even cover. Alexander Kashlinsky and his collaborators had a way to check. Don't chase galaxies one by one. Listen for a whisper in the microwave afterglow. Hot gas in galaxy clusters scatters cosmic microwave background photons. If a cluster is moving relative to the CMB, it adds or subtracts a tiny bit of energy to those photons, the kinematic Sunyaev-Zeldovich effect. The signal is minuscule, buried under the CMB's own primordial ripples and a storm of foreground noise. But statistically, across hundreds of clusters, you can stack and filter. If clusters share a common motion, their KSZ fingerprints should line up into a dipole, slightly warmer on one side, slightly cooler on the other. Get this, they did the stack and claimed they saw it. A surprisingly coherent drift, several hundred up to roughly 1,000 kilometers per second, pointing roughly toward a patch between Centaurus and Vela. The press latched onto the phrase dark flow. It sounded like a hidden river. In talks, Kashlinsky's team pushed the implication. If the drift extended beyond where normal structure could cause it, gravity might be tugging from beyond our observable horizon, maybe relics from inflation, maybe something outside our cosmic patch. The idea turned heads because it punted past the guardrails. It dared you to think about what lay off the edge of the map. Meanwhile, desks filled with plots and skepticism. The KSZ effect is the quietest voice in a very loud room. You have to model cluster gas profiles, subtract foregrounds, choose masks to cut out contaminated CMB regions, filter angular scales, and hope your pipeline isn't inventing patterns. Teams lined up to replicate or refute. Some reanalyses found weaker hints. Others found nothing compelling. The word systematic started appearing in every paragraph. Did the filtering choices preferentially build a dipole? Were residual primary CMB anisotropies fooling the measurement? How robust were the cluster catalogs and their assumed profiles? Planck changed the tone. Full sky maps, higher sensitivity, better control of the microwave sky. When Planck teams applied their own methods, the case for a large-scale, horizon-busting bulk flow thinned to a thread. The claimed amplitude dropped. In many treatments, it vanished into the noise. A Planckiera null result wasn't just a quiet no. It was a statement that, within the instrument's reach and the models applied, there wasn't strong evidence for a universal drift beyond what lambdictum and known structures predict. Conference hallways got lively. Kashlinsky's group defended their pipeline, arguing that specific filters and cluster selections mattered, that Planck's null wasn't a generic death sentence for the effect. Others countered that if a phenomenon needs a particular set of choices to appear, you should get very suspicious. Rival analyses pointed at foreground leakage and profile mismatches. People drew arrows on whiteboards showing how a tiny bias at the filtering stage could leak a primordial CMB dipole back into the measurement and masquerade as KSZ. A micro story from one of those sessions. A postdoc stands at a poster with two panels. Left, their reconstruction with Kashlinsky's filter, there's the dipole. Right, the same data with an alternative filter that better suppresses primary CMB features. The dipole shrinks, then slips within error bars. A senior scientist leans in. So which panel is the universe? The postdoc smiles, tired. The one that survives more ways of being wrong. Here's where it gets important for our river. Even if the dark flow claim fades under Planck's scrutiny, the question it asked was useful. How do we tell local currents from global tilts? Are we mistaking poor subtraction for new physics? The field doubled down on cross-checks. Independent methods, peculiar velocities from distance ladders, density reconstructions from redshift surveys, weak lensing maps, had to line up. If a supposed large-scale flow didn't echo in other tracers, it stayed in the penalty box. While the headlines cooled, our neighborhood map only got sharper. The Dipole Repeller, Shapley tug-of-war, handled the observed local group motion in a way the data liked. Laniakea's flow lines, built from real peculiar velocities, drained past the Great Attractor toward deep structure without calling on super-horizon mysteries. You didn't need a cosmic tilt to explain why our arrows pointed where they did. You needed honest accounting, fewer blind spots, and respect for the quiet power of voids. Still, the lure of an edge-of-the-map influence didn't disappear. It moved into cleaner language, constraints. If there's any residual truly large-scale bulk flow, it has to sit under strict limits from Planck baryon acoustic oscillations and the CMB's tiny anisotropies. Theories that once strutted now tiptoe, labeled as speculative. In this game, humility pays rent. Back at the riverbank, you can feel the pivot. Dark flow was a dare. It forced better tools, tougher pipelines, and sharper questions. In the aftermath, what survived wasn't the rumor, it was the discipline. And that discipline points us back to the currents we can weigh, the pushes we can map, and the basin that quietly through the dust, cracking the zone of avoidance. While the debate over pushes and pulls played out, there was still a blindfold over our eyes. The zone of avoidance wasn't a metaphor. It was the Milky Way's midriff, dust, gas, star fields, smearing and swallowing background light across a wide belt of sky. If you rely on optical surveys, you get a map with a bite taken out of it. And when the missing bite sits on the suspected path of our motion, you misread the river. So astronomers turn to wavelengths that don't care about dust. Hydrogen whispers at 21 centimeters. That HI line slips through the murk and tags neutral gas in galaxies you can't see in starlight. Blind radio surveys swept back and forth across the plain, catching spectral spikes that marked hidden systems. Near-infrared light, less mauled by extinction, filled in stellar mass catalogs where optical images looked like static. And X-rays, almost contemptuous of dust, lit up the hot atmospheres of entire clusters, pointing straight at deep wells of gravity. The payoffs came as names we'd ignored for too long. Norma, Able 3627, stared back from the fog, a rich X-ray bright cluster crouched near the plain. The Centaurus wall, a chain of galaxies strung along a filament, ran like a beam behind the dust. Farther along, observers pulled the Vela Supercluster out of confusion, adding weight to a region we'd treated like rumor. Each detection wasn't just a dot, it was a correction to the force field. But seeing through dust isn't as simple as flipping a switch. Extinction corrections are guesses with math. You build maps of how much light is stolen along each line of sight, then you give it back to your galaxies and hope you didn't tip the scale too far. Near the plane, stars pile on stars, source confusion spikes. HI line profiles overlap, foreground hydrogen in our own galaxy smears across the spectrum, and the clean spike you want gets dented by a neighbor you didn't invite. Distances wobble. And when distance wobbles, peculiar velocity wobbles harder. Here, S where cross-discipline stubbornness saved the plot. Teams didn't trust any one catalog. They stacked them. A galaxy pinged in HI got a near-infrared counterpart. A cluster with an X-ray halo earned a place in the distance ladder. Peculiar velocities calibrated in the clear sky shifted when the same methods were pushed through the dirty belt. You learned where your biases cracked. Then you folded it all into velocity reconstructions that penalized noise but let structure speak. A micro story from a winter campaign. An observer pulls a night shift at a 21-centimeter survey scanning across the galactic plane. The data look like a picket fence, foreground lines everywhere. Then one fence post is wrong, narrow, receding at a speed that doesn't match Milky Way gas. They tag it. Weeks later, an X-ray catalog shows a hot blob in that direction. The two marks line up. A cluster just off the mid-plane gets upgraded from whisper to shout. On the flow map, a shallow basin deepens and the nearby streamlines nudge. Piece by piece, the caricature of the Great Attractor morphed. Behind the blackout curtain lived not a single beast but a crowd, Norma with its entourage, the Centaurus structures threading through, Vela anchoring a flank. Stack them along our line of sight and you get the impression of a singular pull. Spread them out in distance and you see a confluence, midstream structure that matters locally but doesn't own the horizon. There was a cultural shift, too. The Zone of Avoidance had been treated like a permanent scar on our maps, an excuse for why the numbers wouldn't add up. Once radio and infrared made it permeable, that excuse wore out. You could no longer say, "We don't know because dust," without someone replying. Then observe where dust doesn't matter. The cover-up frame landed not as conspiracy but as a reminder. The Milky Way is a bad survey partner if you let it be. Meanwhile, the improved catalog sharpened the boundaries of our basin. Where flows bent around the Centaurus wall, you could draw a line. Where streamlines crossed a shear near Vela, you marked a border. Those borders fed directly into the atlas that would name our home. You could feel it, the way a cartographer must feel tracing a coastline that explorers only guessed at for centuries. One last beat from the fog. An extinction model update nudges brightness corrections by 1/10 of a magnitude across a swath near Norma. Teams rerun distances. A handful of galaxies jump inward. Their peculiar velocities swing from slight recession to slight approach. The local shear eases. An eddy that looked like a separate mini attractor dissolves. You stare at the before and after and realize how thin the line is between a legend and a measurement. With the dust's grip loosened and the hidden scaffolding sketched in, the river's course stopped pretending. The walls and clusters behind the plane didn't end the story. They made it legible. And once the map could move without a blindfold, someone finally drew the orange contour around the true watershed and gave our neighborhood a name. Laniakea, redrawing our cosmic address. Stand back from the tangle and let the river show you the basin. That was the move in 2014. when R. Brent Tully, Hailing Courtois, Yehuda Hoffman, and Daniel Palmer tried something both simple and radical. Define a supercluster not by where matter piles up, but by where motion drains. Instead of counting galaxies and drawing a circle around a dense patch, they trace streamlines, paths a test particle would follow after you subtract the universe's expansion. Where the lines converged, they named a basin of attraction. Where neighboring flows sheared past in opposite directions, they marked a boundary. Then they drew the outer contour that enclosed every flow line headed for our valley. They called that watershed Laniakea, immense heaven. Get this, the map didn't look like the old atlases. It moved. In the Laniakea visualization, individual galaxies sat like bright grains, but the story lived in the white threads. Velocity flow lines turning inward across a region roughly 500 million light-years wide, about 100,000 substantial galaxies pouring toward a gravitational low. And that Great Attractor we treated like a finished line. In the new framing, it flattened into a saddle in the terrain. Locally flat bottom, yes, with its own sphere of influence, but part of a larger slope that guided streams past and on, trending toward a deeper sink downstream. A human beat from that reveal. Tully stands over a rotating 3D render as the orange contour, the watershed rim, locks into place. He points to a sheer plane where neighboring flows peel the other way. That's a border, he says, not a political line, but a kinematic frontier. On one side, galaxies drain into our basin. On the other, they head for someone else. The metaphor lands because it's literal enough. This is a cosmic watershed, and we've been living upstream of a much larger valley than our language ever admitted. Meanwhile, the technique did something trust-building. It didn't ask you to believe a single data source. It fused distance ladders, peculiar velocity catalogs, noise-taming reconstructions, all the stubborn tools we've carried through the dust of the zone of avoidance, into a coherent flow field. If a feature depended on one flaky rung, the shear would ripple and the boundary would waver. Features that survived cross-checks earned their coastlines. Laniakea's borders weren't decorative, they were stress-tested. Here's where it tightens our story. Once you accept motion as the organizing principle, the Great Attractor stops being a mythic destination and becomes a navigational hazard, a midstream low that deflects traffic but doesn't claim it. The streamlines, seen in full, keep bending, following filaments through the Centaurus structures, arcing toward the sector where the Shapley Concentration waits. In that sense, Laniakea doesn't trap us, it situates us. It says, this is the catchment where gravity still wins over expansion on these scales. And within this catchment, the long slope leads away from the saddle and down toward the true heavyweight. A micro-story from the mapping bench. A graduate student toggles the flow integration step size on their screen. Too coarse and the streamlines jitter, missing the sheer boundaries. Too fine and noise masquerades as eddies. They dial it in, watch two neighboring lines diverge cleanly along a plane that slices the Centaurus wall. That plane isn't art, it's a no-go crossing for flows. On one side, waters feed Laniakea. On the other, they drain elsewhere. The room is quiet because a moving border just drew itself. Meanwhile, language caught up. Supercluster used to mean a crowded patch, and we treated Virgo or Hydra, Centaurus as static regions on a density map. Laniakea reframed the term as a dynamic basin. Within it, the Milky Way and the local group still keep their local contracts. Gravity beats expansion on scales up to the group. But at supercluster scales, expansion tries to pull things apart, and motion toward the attractor valley holds them in a loose, flowing association. It's not a bound city, it's a watershed of towns sharing the same downhill. Then comes the consequence that threads back to our earlier clues. If our basin's floor slopes toward Shapley, then our fate lines trend that way too, modulated by dark energy's push and the filament's forks. The Great Attractor's demotion isn't a snub, it's relief. We named the unknown prematurely, the flow field gave it context. The Dipole Repeller's effective push from one side, Shapley's long pull from the other, and Laniakea's boundaries together told a cleaner story. Our CMB dipole, our peculiar speed, our local shear. They all live inside a moving map that finally admits borders. One last human beat. Helen Courtois describes the atlas as the first map that moves. It's not poetry, it's instruction. Because once you see those lines crossing the orange rim and feel the basin like a real valley under a river, you stop pretending our address is a fixed point under fixed stars. We live on a slope. Our neighborhood has edges. And the stream we're in is already choosing a direction, past the saddle we once mistook for the end, toward the deeper gravity downstream. Shapley, the true heavyweight downstream. Follow the streamlines far enough and the river doesn't whisper anymore. It roars. Downstream of the saddle we called the Great Attractor sits a knot in the web that refuses understatement. The Shapley Concentration, the richest concentration of clusters in our corner of the universe. If our neighborhood's motion has a destination, this is the basin that makes compasses honest. Start with what you can count. Redshift surveys sweep that sector and keep tripping over clusters stacked like cordwood. Able numbers pile up. Spectra put them at similar distances, bound by filaments that lace between them. In X-rays, the map glows. Cluster atmospheres, tens of millions of degrees hot, light up like beacons, each one proof of a deep dark matter well. Weak lensing, galaxies behind Shapley stretched into subtle arcs, adds up the invisible mass without asking it to shine. And when you add it all, the totals are blunt. This isn't a local bump, it's a continental divide. Here's the stakes beat we can feel. If mass is the riverbed, Shapley's is carved deep enough to bend streams across hundreds of millions of light years. Velocity reconstructions that let flow lines speak without editorializing keep steering the arrows that way. In the Laniakea Atlas, threads that once curled into the Great Attractor's flat-bottomed basin now keep sliding, arcing toward Shapley's Valley. It isn't just a pretty map. Integrate the flow, and the basin catches traffic. Meanwhile, the data started to say something more specific about our own motion. Take the local group's peculiar velocity budget, how you get from the 600 kilometers per second of our CMB dipole to actual sources. Subtract what nearby walls and clusters behind the zone of avoidance can plausibly provide. Fold in the push from the dipole repellers under density. The remaining vector like Shapley. Different teams, different methods. Peculiar velocity catalogs, Bayesian reconstructions, density to velocity inversions, found their compasses aligning with that basin. A micro story from a lensing group's late night. They stack several cluster fields in the Shapley sector to beat down shape noise. The stacked shear profile rises above the error bars. It doesn't look like a tidy NFW halo. It looks like overlapping halos, filaments, and the connective tissue between them. Someone taps the plot. This is one zip code, they say. We're not measuring a house. We're measuring the neighborhood. Of course, nothing in the cosmic web is a straight road. Between us and Shapley, filaments fork. One path threads through the Centaurus structures we've already met, a corridor of galaxies and groups that feels like an interstate. Another arcs along the longer Perseus, Pisces arm, a different highway running through its own knots and walls. Flow reconstructions can hint at which ramp we've taken, arrows that slightly favor one corridor over the other. But shear planes and local eddies keep the verdict provisional. In some integrations, the traffic merges. In others, it staggers, catching on midstream features before resuming the downhill slide. Complications multiply when you ask how much of our motion Shapley accounts for. Early attempts liked dramatic numbers. Later work got conservative. Under lambdictum, linear theory ties velocity to the gradient of the gravitational potential, modulated by cosmological parameters. In that regime, you can estimate contributions. Local overdensities here, Shapley there. A repeller's underdensity subtracting on the opposite side. Some studies pegged Shapley's share as substantial but not singular, a big piece of the pie, not the whole kitchen. Others emphasized geometry. Even if Shapley's pull is dominant downstream, the path you take around saddles and along filaments decides how cleanly that pull projects onto our measured dipole. But while the number crunching danced, a qualitative truth hardened. The Great Attractor's myth depended on a finish line hidden by dust. Pull the dust curtain back with HI, infrared, and X-rays. Reconstruct the flow with real peculiar velocities. Let voids weigh in with their quiet push. Then follow the streamlines honestly. You end up with Shapley as the true heavyweight downstream. The name matters less than the role. It's the basin your leaves drift toward when they escape local swirls. A human beat from a conference coffee line. Two astronomers trade napkin sketches. One draws the saddle near Norma, a few filaments, a downstream valley. The other draws the same, then adds a subtle bulge off to one side, an intermediate knot that steals attention in some reconstructions. This guy, they say, tapping the bulge, keeps pretending to be the end. The first nods. That's the Great Attractor myth in miniature. Meanwhile, Planck's discipline on dark flow haunted the edges. If there'd been a super-horizon tilt, Shapley might have been a red herring. But with those claims curbed, local structure reclaimed center stage. The river is sloped by things we can, in principle, weigh. The tug-of-war picture, Shapley's pull on one side, the Dipole Repeller's effective push on the other, reproduces the local group's direction without borrowing mysteries from beyond the horizon, consistent with Laniakea's flow-based framing. Now add time. Shapley's basin isn't static. Clusters merge, filaments feed halos, dark energy accelerates expansion and tries to thin the traffic. On supercluster scales, gravity wrestles with that acceleration. Flows slow, but they don't instantly stall. Our fate line, integrated forward, trends toward nodes like Shapley, even if the journey stretches beyond any human calendar. The map we built from today's velocities is a fossil of yesterday's structure, and a forecast that whispers across eons. Here's the consequence that lands like a quiet verdict. The Great Attractor, once a headline, is a midstream rapid that made noise because we stood next to it with poor eyesight. Shapley is the waterfall farther down the valley. Between the two, our path is a set of braided channels, their choices shaped by filaments and shears. And if emptiness on one flank still matters, and it does, it's because it keeps the other side's pull from being canceled. The push makes room for the pull to win. Everything was about to change when we asked a simple question with a hard answer. How far does gravity's claim reach once the universe's expansion pushes back? That's the quiet war our motion keeps score on. The power of nothing, voids as engines. Here's the move that flipped a lot of heads. Treat emptiness like a participant, not a backdrop, a driver. If overdensities are valleys that collect flows, underdensities are hills that shed them. The math is plain. Peculiar velocities trace the gradient of a potential. Where density dips below average, the gradient points away. Galaxies accelerate out, not because they're pushed by a new force, but because everything else pulls harder. The result looks like repulsion. The accounting is gravity. So we started measuring the nothing. Voids aren't circles, they're ragged basins carved by the web. Teams built catalogs from redshift surveys, 6DF, SDSS, 2 mass, marking labyrinths of low galaxy density. Algorithms argued. Watershed methods split one giant cavity into smaller bowls. Spherical underdensity finders merged bowls into bathtubs. Boundaries slid when you changed thresholds. Meanwhile, simulations evacuated mock universes to see how fast walls grew as voids drained. In n-body boxes, particles fled underdensities and streaked along filaments. The pattern matched what our flow reconstructions wanted. Divergence inside voids, convergence along ridges, and currents threading the middle. Get this, when you overlaid reconstructed velocity fields with those void catalogs, the dipole repeller idea gained teeth. Streamlines near our position peeled away from a broad underdensity roughly anti-aligned with Shapley. It wasn't just not enough pull there. It was a coherent divergence zone, a place where arrows refused to point. Integrate test particles through the field and they slid off that hill while curving toward the Shapley Basin. Our speed budget split cleanly. Some fraction from the downstream pull, some from the upstream absence. A micro-story from a simulation lab. A grad student seeds tracer particles in a cube carved from the local universe. They color them by initial position: blue near the suspected repeller, orange near the Shapley side. As the code integrates, blue tracers fan outward and skim the walls, orange tracers swirl inward and stack in knots. The room gets quiet because the motion looks like the map we built from real peculiar velocities. The nothing behaves like a hill. Meanwhile, observers pin the scaffolding around these cavities. Cosmic voids aren't empty of clues. They imprint weak lensing signals, subtle anti-shears where background galaxies experience less focusing than average. Stack enough voids and the underlensing shows. Cross-correlation of galaxy positions with CMB maps found the integrated SACs, Wolf imprint of evolving potentials, slight temperature shifts where voids and clusters tug on photons in a universe with dark energy. Those signatures don't hand you a single repeller address, but they say the void physics we're relying on is operating in the sky we measure. Here S where language tried to sabotage us again. Repeller sounded dramatic. The field fought to keep it honest. Papers leaned on phrases like effective repulsion and underdensity-driven divergence. Colloquia came with disclaimers: no anti-gravity, no exotic fields, just lambdictum gravity rearranging traffic. The payoff for the semantic discipline was precision. When you tell people what a word doesn't mean, they remember what it does. But voids aren't polite when you push for numbers. Identify one with spherical cuts and you'll underestimate its power. Slice with watershed plains and the hilltop fattens. Change the density threshold and the rim moves. Two catalogs drawn from the same redshift survey can disagree on how many supervoids span a region. So the community built ensembles. If a divergence feature in the velocity field lined up with different void finder ridgelines, it got promoted. If it only existed under one algorithm, it stayed on probation. A micro-story from the catalog trenches. A team runs 3 void finders on a 2-mass-derived volume. The first paints a huge, lumpy basin, the second slices it into 3, the third misses a wing near the plane. They overlay all 3 with their reconstructed shear field. 2 of the candidate rims match a high shear sheet, the third doesn't. They throw out the odd one, keep the common ground, and the inferred repeller footprint shrinks but deepens. Less area, more certainty. Meanwhile, the broader lesson kept repeating. Model growth of structure with and without proper void treatment, and you mispredict flows, misread weak lensing, and skew bulk motion estimates. Overdensities don't operate in a vacuum, literally. Their reach depends on what isn't around them. Our local group's direction only made full sense when the map admitted the hill on one side and the valley on the other. Here's the stakes line you can carry. If you ignore nothing, you'll get everything wrong. Voids set the gradients that make clusters matter at the distances they do. They gate which filaments carry who and how quickly. They're the quiet half of the riverbed. And with that quiet half in place, a final pivot becomes possible. Now that we can weigh pulls and trace the effective push of absence, what does the future flow look like once cosmic expansion keeps pushing back? That's the war our motion's been quietly scoring since the day we named the myths and mistook it for an flow carries the local group. So where does the river take us? Not in headlines or headlines' lifetimes, but in slow, stubborn motion measured against the expansion of space itself. Fate here isn't prophecy, it's integration. You take today's velocity field, subtract the Hubble stretch, follow the gradient of the potential, and march a tracer forward. One step at a time, you let the current choose. Start small. On scales of a few million light years, gravity is king. The Milky Way and Andromeda are already committed to each other. Their peculiar motion ignores expansion, and in a few billion years they'll merge into one halo, a local settlement on the riverbank with its own weather. That's the neighborhood contract, bound despite the universe's push. Shift to supercluster scales and the rules bend. Expansion matters. Dark energy, the late-time acceleration baked into lambdictum, adds a gentle, persistent tug outward, thinning traffic and shallowing gravity's wells. The question becomes a balance sheet. Is the downhill slope toward Shapley steep enough and broad enough to keep drawing us in while the page we're scribbling on stretches underneath? Here's the clean way we test it. You integrate test particles through a reconstructed flow field that's anchored by data, peculiar velocities, redshift densities, lensing hints. Then evolve the field forward under linear theory where it holds and with simulations where it doesn't. Every step acknowledges that halos grow as filaments feed them, that clusters merge, that the riverbed changes shape even as water runs downhill. It's not perfect prophecy, it's disciplined extrapolation. What the integrations say is both modest and firm. Our streamlines keep bending toward deeper nodes, toward Shapley's basin, though the rate of approach slows with time. Dark energy doesn't flip the direction, it drags the brakes. In a decelerating universe, you'd expect more dramatic infall, richer merging of supercluster-scale structures. In this one, infall persists along filaments where overdensities carve channels, but much of the low-density countryside gets stranded. Islands of structure keep their influence. Oceans of emptiness get wider. A micro-story from a code run. A researcher seeds a cloud of tracers around the local group's present coordinates and lets them flow in a field that includes the Dipole Repeller Hill and the Shapley Valley. Early on, the cloud elongates, sheer near the saddle stretches it. Farther downstream, the strands converge along a filament threading the Centaurus structures. Advance a few billion years of simulated time and the cloud is a ribbon, its head nudging deeper into the Shapley slope, its tail still feeling the hill behind. The researcher rewinds, toggles dark energy off. The ribbon collapses faster, toggle it on again. The ribbon still points the same way, it just arrives late. Meanwhile, the route isn't a straight shoot. Filaments fork, saddles deflect, side basins borrow traffic. One corridor pulls us through Centaurus, another tempts along a Perseus-Pisces arc. Sheer plains mark no crossing zones, yet local eddies churn where midstream knots grow. That's the humility beat. Fate lines aren't highways with exit numbers, they're braided channels. The headline stays, downstream trends toward Shapley, but the exact strand we surf can wander. There's a human reason this matters. When we say address, we aren't just naming a dot, we're naming a direction. In Laniakea's atlas, boundaries aren't walls, they're shears where neighboring flows head elsewhere. If over cosmic time our streamline stays within this basin, then our identity as part of this moving watershed holds, even as expansion tries to fray associations. If a future shear migration were possible, if changing mass distribution redrew borders, then a sliver of the cloud might peel away. The integrations don't favor a jailbreak. They favor continuity. The basin persists as a kinematic home, and within it, the downstream slope keeps its tilt. Now the uneasy part. Timescales dwarf every story we can tell with breath. 1 billion years is a chapter, 10 billion is a book. On those scales, local headlines, mergers, starbursts, quenching dot our path, but the river's direction isn't set by any single event. It's set by the shape of the potential carved by everything around us. That's why the Dipole Repeller still matters here. Its underdensity by lightening one flank keeps the downstream projection clean. Take the hill away in the model and our arrow wobbles. Put it back and the streamlines settle. There's a counter question that stays honest. Could dark energy's acceleration grow so dominant that large-scale infall effectively stalls, trapping us near a saddle? In lambdictum present parameters, the answer bends towards slowed, not stopped. Nodes keep gaining mass from the filaments that have already formed. Peculiar velocities damp, but gradients endure where contrast is high. Our forward integrated paths creep, but they don't reverse. Fate becomes asymptotic. Approach without dramatic capture, a drift that feels like longing stretched across expansion. A final micro-story to hold onto. 2 plots on a screen. Left, present-day velocity field, our arrow drawn. Right, a projected field several billion years out under the same cosmology with updated masses from a semi-analytic growth model. The arrow on the right is shorter, dark energy's handwriting, but it points the same way. A note in the margin reads, direction costs less than speed. That's the quiet verdict. Gravity writes our route, expansion edits the pacing. The local group's fate line stays threaded through a basin that trends toward Shapley, grazes saddles, respects shears, and feels the lift of an emptiness at its back. It won't make our calendars. It will make our address. Gravity versus expansion, the quiet war. Everything we've mapped, pulls, pushes, basins, borders, lives on top of a larger contest. Gravity wants to gather. Expansion wants to separate. Our motion is the scorecard of that quiet war. Start with the split personality of a galaxy's redshift. Part of what we measure is the Hubble flow, the recession from the expansion of space. The rest is the peculiar velocity, the darting motion through that expanding fabric, guided by gravity's gradients. Confuse the two and you'll misread the river. Separate them cleanly and the currents appear. Here's the rulebook in plain terms. On big, mostly linear scales, peculiar velocities trace the gradient of a potential set by mass contrasts. Overdensities sink the potential, underdensities raise it. The velocity field points downhill. That's why reconstructed streamlines behave. Galaxies follow slopes carved by clusters and voids. But zoom in to nonlinear knots, clusters, groups, merging halos, and gravity stops asking permission from the expansion. Locally binding wins. Globally stretching keeps pulling. Now remember dark energy, the late-time accelerant. It doesn't tug like mass. It changes the background against which all motion plays. The Hubble flow gets a gentle boost. Peculiar velocities feel drag because contrast grows more slowly when space stretches faster. Put differently, the riverbed still slopes, but the page it's drawn on keeps widening. A micro story from the pipeline that makes this real. An analyst feeds the same peculiar velocity catalog through two cosmologies, one with today's dark energy density, one dialed to 0. The linear growth factor changes. The Wiener filter breathes differently. In the no, dark energy run flows bite harder into attractors, streamlines steepen and converge sooner. Restore dark energy and the same threads arc more languidly. Directions hold, speeds shrink. The analyst circles identical arrows at two epochs and writes, slope same, slide slower. Meanwhile, separating signal from artifact isn't optional. Backreaction debates try to argue that inhomogeneities could mimic acceleration, that clumpy structure might change the average expansion enough to fool us. But the CMB's precise anisotropies, baryon acoustic oscillations, supernova distances, and lensing convergence maps cohere under lambdacdom. That coherence is the guardrail. We let peculiar velocities trace density, but we keep them anchored to a background expansion nailed down by independent probes. Here's where mistakes sneak in. If you fit a bulk flow without correctly subtracting the Hubble component, if your distances are biased, you're 0 point off. You'll see currents that aren't there. If you try to extend a nonlinear model too far out, you'll overpredict infall where linear theory should rule. The reverse is just as bad. Apply linear assumptions in a cluster core and you'll sand down real, sharp accelerations into mush. The fix is humility baked into code. Switch regimes when the math tells you to. Let linear reconstructions map the broad slopes. Hand the knots to simulations and dynamical models. A human beat from a cross-check meeting. One team presents a bulk flow measured from distance ladders. Another shows a density-to-velocity inversion from a redshift survey. A third flashes weak lensing shear around known attractors. The arrows don't perfectly overlap, but the field leans the same way. Someone points at a mismatch near a shear plane. Linear versus nonlinear boundary, they say. Heads nod. The disagreement shrinks from existential to expected. Meanwhile, our local ledger gets cleaner when we respect this split. The Dipole Repeller's contribution shows up as a broad divergence, squarely a linear scale feature. Shapley's pull blends both regimes, long-range linear guidance into the basin, plus nonlinear acceleration inside clustered knots. The Great Attractor's saddle acts locally nonlinear, but sits on a linear slope that trends past it. Treat them with the wrong math, and you'll either overstate a legend or underweight a basin. Here's a tidy test that earned trust. Take the reconstructed velocity field that fits peculiar motions today. Forward model the kinematic Sunyaev-Zeldovich imprint. Those velocities would paint on the CMB tiny temperature shifts from cluster gas in motion. Compare to Planck's KSZ constraints. If your flows were fantasy, the predicted KSZ dipole would be off. Instead, within uncertainties, the match holds. Different messenger, same story. Gravity sculpts peculiar velocities. Expansion sets the stage. The microwave sky nods along. So what's the takeaway you can carry without a blackboard? Gravity writes the directions, expansion edits the cadence. In linear stretches, flows obey the slope. In tangled knots, binding ignores the stretch. Our local group's arrow is a fossil of both. Yesterday's clustering carving today's slope, today's acceleration stretching tomorrow's stride. Get the balance wrong and the map lies. Get it right and the river tells you where it's going, even as the banks slowly pull apart. Beyond the horizon, speculations and strict lines. There's a temptation baked into any map. Stare at the edge long enough and your brain invents coastlines beyond it. The dark flow rumor fed that impulse. What if something outside our observable patch tugs on everything inside? The pull of a hidden continent is a great story. The problem is, stories need guardrails. Start with the ground we trust. Structures like Shapley and voids like the Dipole Repeller grow from tiny, nearly scale-invariant ripples seeded in the early universe. Inflation, an ultra-brief burst of expansion, stretched quantum fluctuations to cosmic sizes, freezing them into the initial conditions we still read in the cosmic microwave background. Lambdictum takes that seed field, adds cold, dark matter and dark energy and says, let gravity sculpt. On those terms, our local currents make sense without borrowing from beyond the horizon. Now here's the space for speculation that doesn't break the rails. Inflation didn't promise a tidy ending everywhere at once. Many models allow cosmic variance, statistical wiggles on large scales that can make one patch of the universe a little denser or a little emptier than average. In principle, those superhorizon modes can tilt the playing field slightly in any given region. If you're unlucky, your patch sees a gentle net drift, but gentle is the keyword. Planck's CMB maps, baryon acoustic oscillations in galaxy surveys and large-scale lensing all agree. Any such tilt has to be small, not zero, small. This is where dark flow ran headlong into the wall. A coherent 1,000 km/s drift across gigaparsecs would demand a superhorizon structure big and lopsided enough to splash the CMB with obvious asymmetries. Planck didn't see those. The low multipole oddities people argue about, the quadrupole's phase, a hemispherical power asymmetry, live at the edge of statistical patience, but they don't license a universal current of that size. Strict lines mean this. If your claim needs the CMB to look different than it does, your claim sits outside the fence. Meanwhile, there's a class of ideas that exploit inflation's habit of making more space than we can see. You'll hear about multiverses, pocket universes budding off like soap bubbles, each with its own constants. Could a neighboring bubble's gravity yank on us? The romance is strong, but the math is cruel. A bubble collision leaves a specific scar, a disk-like modulation in the CMB temperature and polarization. Searches have hunted those fingerprints for years. So far, nothing conclusive. The strict line here is the same. If the sky doesn't carry the bruise, you can't claim the punch. Other proposals try to tweak gravity itself. What if on very large scales, gravity departs from Einstein's script and falls off differently? Modified gravity models can change growth rates, shift how potentials evolve, and in principle, alter bulk flows. But they don't get a free pass either. The same models must match lensing, galaxy clustering, redshift space distortions, and the CMB's lensing potential. Many fall apart under that crossfire. A few survive with tuned parameters that end up looking an awful lot like standard gravity plus dark energy. The rule we live by. New physics has to explain everything the old physics already nails, and then improve one stubborn mismatch without inventing others. There's also the lure of ancient relics, textures, cosmic strings, topological defects from phase transitions in the early universe. They tug on matter and light, leaving step-like features or line-like lensing signatures. Surveys have searched, constraints have tightened. If any remain, their gravitational fingerprints are too faint to steer our entire basin. Strict line. You can keep them in a sidebar. You can't lean your flow map on them. A micro story from a theory group meeting. A young researcher pitches a model where a very long wavelength mode beyond our horizon biases local flows by a few dozen kilometers per second. The senior folks nod, plausible under cosmic variance, consistent with Planck. Then the same researcher pushes the amplitude higher to chase the original dark flow. A hand goes up. The CMB would light up, someone says. The room recalibrates. The first version survives, the second gets shelved. Here's the real payoff of drawing lines. It forces the field to separate wonder from wish. We keep the curiosity, what lives beyond the last scatter of our light. But we let measured constraints hold the pen. When a provocative claim shows up, we don't swat it down for being daring. We ask whether it survives more ways of being wrong. KSZ stacks with different filters, peculiar velocities from independent ladders, density reconstructions checked against lensing, CMB imprints that match the implied potentials. And sometimes the answer is a clean no. Planck's nulls on a horizon-busting dark flow pulled that rumor off the main stage. Good. That's how science trims its stories. In the space left behind, the map we can test breathes easier. Laniakea's basin defined by motion, Shapley's pull measured by clusters and lensing, the Dipole Repeller's hill traced by divergence. No extra continents required. One last human beat, because this is how progress feels. A conference panel fields the inevitable what-if about a beyond-the-horizon tug. The moderator smiles. If it leaves a measurable trace, we'll see it, they say. Until then, we have plenty to explain with what's on the page. Then they point back at the moving atlas, the one where borders are shears and names are earned by motion. The room doesn't stop wondering. It just agrees to wonder inside the lines and to let the tools that bent the night, how we measured the invisible. If motion is the handwriting, tools are the penmanship class. None of this, repellers, basins, downstream pulls, works without methods that argue with themselves and still agree. Trust comes from error bars. Meaning comes from cross-checks that survive them. Start with distances, because every velocity depends on them. Cepheid variables, stars that brighten and dim with a period tied to their true luminosity, set the nearby rungs. Type Ia supernovae, standard candles when corrected for light curve shape and color, extend the reach. For spirals, the Tully-Fisher relation turns rotation speed into intrinsic brightness. Measure the line width in HI at 21 centimeters. Get a distance once you correct for inclination and extinction. For ellipticals, surface brightness fluctuations exploit the graininess of unresolved stars. Closer galaxies look noisier, farther ones smoother. Each rung has systematics, metallicity in Cepheids, dust in supernova hosts, inclination errors in Tully-Fisher, stellar population variations in SBF. So teams recalibrate, cross-match, and refuse to let one ladder set the scale alone. Meanwhile, you need mass. X-ray telescopes weigh clusters by reading the temperature and density of hot gas trapped in their dark matter wells. Hotter gas means deeper potentials. Weak gravitational lensing sidesteps baryons entirely. Background galaxies shear as their light crosses invisible valleys. And with enough statistics, you can map the mass without asking it to glow. Redshift surveys trace the skeleton, SDSS, 2 mass, 6 DF, where galaxies outline filaments and walls. Convert those luminous tracers to a density field with careful bias modeling, and you've got the bones to compare against the muscles of motion. Then there's the whisper in the microwave sky, the thermal Sunyaev-Zeldovich effect, CMB photons gaining energy off hot electrons in clusters, flags halos independent of redshift populating catalogs that pierce the zone of avoidance. The kinematic SZ is the subtler sibling, Clusters moving relative to the CMB nudge photon energies up or down by tiny amounts. A velocity tracer that, when stacked carefully, tests whether your reconstructed flows are plausible. Planck's full sky maps gave both a proving ground and a referee. Claims that leaned too hard on wishful filtering, dark flow's loudest versions, faded when Planck's nulls arrived. Here's the brain of the operation, turning a scatter of imperfect distances and redshifts into a velocity field that doesn't hallucinate. Bayesian reconstructions, often built around Wiener filtering, assume linear theory where it holds. Peculiar velocities trace the gradient of a potential that itself follows from density. Feed in data with their errors. Out comes a smoothed field that respects uncertainty. Local nonlinear knots, cluster cores, merging groups, get flagged for special treatment or sidelined so they don't poison the global slope. The output isn't a picture, it's a discipline. Valleys where flows converge, hills where they peel, shears that mark borders between basins. Microstory from a code sprint. 3 teams sit around a table with coffee gone cold. One has Tully-Fisher distances heavy in the south. One brings in SBF for ellipticals near the plane. The third folds in supernovae that arc towards Centaurus. Each runs an independent reconstruction. On a shared screen, they layer the streamlines. In one corner, an eddy that appeared in an early map vanishes across all 3. In another, a sheet of shear survives every cut. Someone draws a line with a stylus. That's a border, they say. The room exhales because the map just earned a contour by consensus, not by charisma. Crosschecks keep score. Take the reconstructed flows and forward model the KSZ imprint clusters should stamp on the CMB. Compare to Planck's constraints. If the predicted dipole blows past the data, your field's overconfident. It doesn't. Within uncertainties, the amplitudes play nice. Or project your density-derived velocity field onto the directions highlighted by weak lensing convergence. Mass along a line of sight should pull flows its way. The alignments aren't perfect, noise, nonlinearity, but they rhyme. That rhyme is the sound of method beating myth. Meanwhile, the zone of avoidance loses its veto when tools stack. High at 21 centimeters tags Galaxies the optical sky hides. Near-infrared light shrugs at dusk and tightens distance moduli. X-ray catalogs drop cluster pins where star fields look like static. Feed these into the same reconstruction machinery, and what used to be a blindfold becomes a blur you can debias. And when a bold claim fails a tool gauntlet, it steps aside. Dark flow's strongest version stumbled under Planck's view and alternative filters. The Dipole Repeller, by contrast, didn't arrive by fiat. It emerged from divergence in the velocity field, then found circumstantial support where void catalogs and shear sheets overlapped. Laniakea didn't depend on a single rung. It depended on flow lines that survived being measured 3 different wrong ways. Here's the payoff you can feel in your bones. We didn't conjure a moving atlas by wishing. We earned it by letting methods argue until only the shared features stayed. Standard candles, standard rulers, hot gas, bent light, galaxy counts, microwave whispers, and Bayesian glue. Together they bent the night enough to reveal the river underneath. And once the river was visible, the names on the map had to change. The meaning of a moving home. There's a moment that keeps replaying in this story. You think you've named the force that guides you, then the map moves and your name shrinks. That's not failure. That's how a living atlas grows. Start with a small room and a bigger argument. A young researcher puts a printout on the table, streamlines wrapping the Great Attractor's saddle, then bending on, pointing toward Shapley. Someone who spent a decade defending Ga as the destination looks at the lines and laughs once short. All right, they say, it's a bend, not the bottom. The word attractor doesn't get erased, it gets demoted. The room doesn't lose certainty. It trades a myth for a mechanism. Then there's the day humility became a tool. A team chases the dark flow dipole through a KSZ pipeline built from WMAP-era habits, stacks clusters, and watches a dipole rise. Momentum builds until Planck's sky lands on the desk. Same idea, stricter masks, different filters, better noise control. The dipole thins, then dissolves within the bars. At a conference mic, a voice says, "No." The claim doesn't die angry, it walks off and pushes everyone to calibrate harder. The payoff isn't a discovery, it's discipline that spills into everything else. Meanwhile, the galaxy keeps trying to mislead us. A distance ladder update slides extinction corrections by a hair through the zone of avoidance. A few galaxies near Norma step closer. Their inferred peculiar velocities flip sign, and a local eddy on the flow map vanishes. The scientist who'd been grooming that eddy as a mini attractor shrugs and moves the marker. "Dust was lying to me," they say, and they sound relieved. You can't keep a legend alive once a cleaner method sweeps its stage. Thread these beats and the lesson is personal. We don't live at a fixed coordinate with a tidy label. We live inside a current, and our address is a direction as much as a place. Laniakea didn't hand us a new zip code. It taught us to speak in slopes and shears. The Dipole Repeller didn't smuggle in exotic physics. It taught us to count absence as action. Shapley didn't appear because we wanted a bigger monster. It earned the role by bending lines that passed every cross-check we could throw at them. Here, where the language we use changes us. Great Attractor was a guess, a banner you plant when the fog won't lift. Keep the banner too long and you start saluting it. Let it fall when the map moves and you get something better, a basin that moves you, a slope that explains why your compass doesn't point at the sign you painted. Names help us tell the story. They shouldn't be allowed to write it. A micro story to carry home. A kid in a planetarium asks where the Milky Way is going. The presenter used to say, "Toward the Great Attractor," and leave it there. Now they take a beat. "We're sliding down a long slope," they say, "past a shallow dip we once mistook for the end, steered by a deep valley far downstream and kept honest by a hill of nothing on our back." The room is quiet for a second. Then the kid says, "So we're in a river." The answer lands. Exactly. Meanwhile, the field keeps its guard up. When someone waves a new anomaly, the first question is, what if? It's, does it survive more ways of being wrong? That habit born in the dark flow fights, hardened by ZOA corrections, validated by lensing overlays, turns into culture. The culture draws strict lines around speculation, not to strangle wonder, but to protect it from shortcuts. Wonder that passes a test lasts longer. And there's one more thread that makes this feel human. The people who argued hardest about where we're going often end up co-authoring the map that proves them partially wrong. It's not contrition, it's momentum. Rival ladders get merged. Independent reconstructions land on the same sheer sheet. The orange contour around Laniakea's watershed doesn't bear a single signature. It bears a truce. So what's the meaning of a moving home? It's not that we learned our destination. It's that we learned to treat direction as data, not dogma. Our galaxy isn't wandering. It's being steered by poles we can weigh and voids we can't touch, and our names have to keep pace with the flow. Keep the humility, keep the cross-checks, keep the borders that move, and the river will keep telling the truth, even when our labels don't. The quiet verdict is simple. Our home drifts along a real slope, shaped by clustered mass and carved by emptiness, past a myth we named too early toward a basin we can finally trace. If you want to see where these currents reshape galaxies from the inside, black hole feeding, star formation throttled by environment, watch our follow-up right here. Subscribe if you want the next untold turn in this river, the stories that live at the edge of what data can prove. And remember, one tiny asymmetry at the bottom of the CMB dipole still waits on the map's fringe.